Now here I would like to start with the procedure, how we deal with it. Have a look. If you are given a scalar value in this way, okay, scalar function, which is function of x, y, z, okay, and now this three variables, which is phi, we want to differentiate by finding the gradient of phi. So what we are going to do, we will apply this del on this phi. As you can see, gradient phi is del phi. So what will happen now? It will apply on I element, j element, k element in a way that we differentiate phi with respect to x multiplied by I. Because what happened is here is dot. It's like dot product. So I element, j element, k element, as we discussed before. We differentiate phi with respect to y. We differentiate phi with respect to z. Okay? It gives at the end vector. So phi we started with scalar, but at the end when we find the gradient or del phi, we found vector. Now example, you are given this scalar function which contain x, y, z. And he wants me to find the gradient phi at this point 1, 3, 2, which represent x, y, z respectively. So what I will do, I will differentiate this function with respect to x first, with respect to y second, with respect to z third. How I do this? With respect to x, you see the first part here, these two elements, I will keep them constant. I will don't touch them, because I will differentiate only with respect to x. So x squared, it will be 2x. The same thing here. These two elements, I keep them. I will differentiate only x. Differentiation of x is 1. By them, we will keep them. I repeat the same thing here. Here I will differentiate with respect to y. So it means x and z will be keep constant. Here I differentiate with respect to z. It means x and y will keep constant. So I got elements for each one of these partial differentiation. Now I will substitute here this part by I, this part by j, this part by k. Now next and the final point is to substitute p, which is the point given to you, x, y, z in each element. You see here I substituted for this x, this y, this z everywhere by their values. My advice here is to use brackets, because the brackets will reduce the error problems, or let me say you may forget sign, you may forget number. Okay, it will reduce the mistakes and not mixing the numbers. So I do the math here, and this is the final shape of my gradient, which is vector. Now what I want you to do, I change the function here phi, and I change the point. I give you here hint how to go through the steps. So go through these steps at home, try to find the values here and here and here, and then substitute. Then substitute the point x, y, z in the final gradient. The final answer I gave you here just to check your results to see if you are right or wrong. Now properties for gradient, del a plus b, it will be del a plus del b, and del a dot ab, it will be a del b plus b del a. This is their properties for gradient of scalar. The next point is directional derivative. Directional derivative, as just example to make it close to your mind, when we have a scalar in the direction of vector. As example, we have charge, electrical charge in electrical field. Okay, so electrical is the vector, charge is the scalar, and then it's moving in the direction. So how we find the directional derivative of scalar in the direction of vector? We have formula here. Let's say we have phi, which is the scalar, and a is the vector. Then directional derivative of scalar in the direction of vector, d phi over ds call, is a dot gradient phi. Just a minute, this is dot product, so it gives scalar or vector. You remember we say it's scalar. At the end I will have a scalar. Okay, great. Now gradient phi, it means del phi. We already discussed it in the last few slides. What is a? A as a vector. It's unit vector. In the unit vector in this way, dr on its magnitude. I will explain it through this example. Let me see the example. he told me here, compute the directional derivative of phi. Phi is a scalar. At the point, he gave me point. In the direction of vector, he gave me vector. First, I will find the gradient. Gradient d del phi. We learn how to find del phi. Okay, this is phi. Then I will differentiate phi. Where is it? It's given in the question here. With respect to x multiplied by I, with respect to y multiplied by j, with respect to z multiplied by k. I am here now at this point. Now I will substitute the value of point x, y, z. As you can see here, we learned this, we already solved the problem. So this is the gradient. Now next, this is the vector. Let me find the magnitude of the vector. So 2 square plus 3 square plus minus 4 square, all under square root. This is the magnitude. Now a, which is what I'm looking for, is the vector divided by its magnitude. So I just need to divide the values, as you can see, 2, 3, minus 4, by its magnitude here. Now I prepared a, I prepared del phi, so I just need to do the dot product. It means I element here with I element here, multiply them. J element with J element, multiply them. K element with K element, multiply them. You see I, J, K already disappeared, so at the end we come up with what? With a scalar. Next point, I have more 2 points to complete this session, is unit normal vector. Unit normal vector, when we have a scalar which is equal to constant, as example 0, okay? Now, a derivative of this scalar will give 0. So if I say, as example, del r gradient phi equals 0, then this is dot product, then magnitude of the first element here, magnitude of the second element here, cosine the angle between them should equal 0. And this happens when cosine theta equals 0. I'm talking about the theorem from when it came. So cosine theta, when it comes 0, when theta equal 90, which means that it is normal vector. It means they're perpendicular. Okay. And unit normal vector at the end, okay, will be dot product, so it will give scalar. Now, with example, it will be clarified here. Have a look here. The unit normal vector, and for x, or this phi. As you can see here, I will find del phi. Okay, so I will apply partial over partial x for this formula, multiply by I, and for this formula with respect to y, multiply by j, and this formula multiply by with respect to z, multiply by k, and then I will substitute the point x, y, z here and simplify. We got vector. Now the magnitude of this vector is 2 square plus 1 square plus 1 square under square root. I got it. The unit normal vector is to divide the del vector over its magnitude, as you can see here. Last point here is divergence of vector. Divergence and convergence, okay, when we come close we say this is convergence, and going far from each other we call divergence. It happens in many parts of the science and engineer. And just to clarify, through this arrow you can see here, this arrow, they are opposite, they never meet, and these arrow opposite, these arrows, they move in a constant speed, they will not meet at all. This one, so this is again divergence. Okay, here you can, these are opposite, but you see this one, it come from here, it go from here, this one it come from here, go from here, but these two, as you can see, they are come close to each other. Okay, so they will meet, we could say this is convergence because they will meet somewhere. Now if we take this idea in vectors, if we have vector a, the divergence of a, okay, is, I'm talking about divergence and convergence now. No, divergence of a is div, which is div, is del dot a. Just a minute, dot, it means we will come up with a scalar. Yes, correct. Del, we have del, we know del, we solve problems, and a is given in the question, so it's very easy, direct forward. We do the dot product. we come up with a scalar. Now one note to be mentioned here, if the div A, the divergence, is equal to 0, we'll call A to be solenoidal vector. Only and only if it equals 0. Example, this is A, as you can see here, and he gave you the point, he asked you to find div. Dot product, very easy and direct. Okay? We differentiate with respect to x, with respect to y, with respect to z. As you can see here, this element with respect to x, this element with respect to y, this element with respect to z, and we come up here. Then substitute the point x, y, z, and find the div. It's 13, so it's not solenoid. This is exercise. I just changed the function and the point, and you need to follow. I gave you here the final answer. Try to find the same value. Now here, I would like to close this session. We will continue in the next session, but I will close it with this exercise to enjoy it at home to solve some problems. See you next session. Thank you.